Hello, and welcome to week number 9, BC Calculus. Let's begin. Last week we were talking about instantaneous rate of change, acceleration, when is particle at rest, displacement, and stuff like that. I'd like to just go through a problem that's very similar to the one that we were talking about. It says a particle moves along a horizontal line so that its position at time t is greater than 0 is given by, and it gives you a position function. So this, I always consider these to be position functions. So my position function at any given time is equal to negative t to the third plus 7t squared minus 14t plus 8. Okay, and then it says find the instantaneous velocity when time t is equal to. Well, instantaneous velocity is the first derivative of position. So I'm going to find the velocity function, which is negative 3t squared plus 14t minus 14. And now all I have to do is plug in 2 into here. And when I do that, I end up with, let's see here. So if I put 2 in here, that gives me 4. That's negative 12 plus 28 minus 14. Oops. So that gives me negative 26 plus 28. So that gives me 2. So the velocity at time 2 is equal to 2. Hello, Caleb. How are you doing today? Then the second part, it says find the acceleration of the particle at time t is equal to when t is equal. Well, acceleration is the next derivative from velocity. Sick. Oh, why aren't you sleeping? You can always watch the recording. And plus, anyways, most of the stuff you guys already know. So we have acceleration is the next derivative from velocity, so that gives me negative 6t plus 14. If I put 2 in there, I end up with the acceleration at 2 is equal to negative 12 plus 4, which is also 2. When is the particle at rest? Well, when we want to find when a particle is at rest, we always find when the velocity is equal to 0. So I'm going to set my velocity function, so negative 3t squared plus 14t minus 14 equal to 0. And I'm going to solve that. Well, in order to solve this, I'm going to have to factor. Well, factoring, if I multiply the two outer terms together, what does that give me? 14 times 3, so that's going to be 42. And then what two numbers multiply to give me 42 that add up to 14? Let's see here. Got to be something. Well, I guess it doesn't have to be. So I use, because I'm factoring, and I guess it doesn't have to be because we can use a graphics calculator to figure out what the solution is there. I'm just wondering if it does have a solution. So that's 42. We've got 6 and 7. That doesn't work. I'm not seeing anything that would work there. I'm not sure it would. So that means I'd have to just take my calculator, plug this into my calculator, and then graph it out, and you'll see that it's going to cross the x-axis in 2 different places, or it's going to, well, probably will cross in 2 different places because it is a parabola, it's opening down, and that would be the time in seconds that it would take to hit the ground. And again, I'm going to have my calculator, so this problem gets a whole lot harder, because then it says find the displacement of the particle during the first 2 seconds. Well, displacement is total distance travel, or from where you start to where you stop. So I'd have to find S of 0, and S of 0 is pretty easy. That's just 8. And then S of 2, well, let's see here. If I put 2 in there, that gives me negative 8 plus 4 times 7. That's 28 minus 28 plus 8. That's 0. So that was pretty easy. So the displacement would be 8 minus 0 over the total time. So my displacement would be 4. So that is how we would do a particle motion type problem. You just have to, understand that you have position. First, the derivative of position is velocity. The derivative of velocity is acceleration. Then we also talked about related rates last week, finding the related rate of a problem. In this one, it says two cars are traveling along along perpendicular roads. Okay, so I know what perpendicular is. Okay, so this is car A at 40 miles per hour, car B at 60 miles per hour. At noon, when car A reaches the intersection, okay, so this is car A at the intersection, car B is 90 miles away. Okay, so let's say he's down here. So this is 90 miles here. This is car B. This is car A. And it says, and moving toward it. Find the rate at which the distance between the cars is changing at 1 o'clock. Well, that means car A is going to travel 1 hour at 40 miles per hour, so this is going to be 40. And that means car B is going to travel 60 miles. Well, it started at 90 miles out, so this is going to end up at 30 miles. So I'm looking for this, how fast this is changing. So let's call this C. So this is going to be A. So I know what dA dt is. That is 40 miles per hour, and A is equal to 40. And then dA dt, I'm sorry, dB dt, car B was traveling at 60 miles an hour, right? So that's 60, and B is equal to 30. I don't need this 90 anymore. So then I have A squared plus B squared equals C squared. So this is going to be 2A dA dt plus 2B dB dt is equal to 2C dC dt. Now, I do need to know what C is, and since these are perfect squares, this would be 50, wouldn't it? So I'm looking for that. So now all I have to do is plug everything. So 2 times 40 times 40 plus 2 times B, which is 30, times the rate it's traveling at, it's 60, is equal to 2 times C, which is 50, dC dt. And then I just have to solve this. And without a calculator, I'll let you guys solve it yourselves. I definitely need to, I don't know what's wrong with my graphics calculator. Every time I turn it on, the screen goes blank. I change the batteries, still not good. All right. So that's how I would set that problem up to solve. Caleb, any questions so far? All right. Now this week, we're going to talk about linearization and L'Hopital's formula. Two very simple things to work on. Shouldn't cause you any problems this week. This week is a short week. It's only 4 days long. You guys have Thursday and Friday off because it is a short week. Teachers have faculty meeting on Monday, or I'm sorry, on Thursday, and then we also get Friday off. Yay! All right. Linearization. Linearization. This is the formula for linearization. It says L of x, which L stands for linear, is equal to f of a plus f prime of a, x minus a. Okay, now, whenever I see linearization in a problem, all I think about is a tangent line, because a tangent line is exactly the same thing. If you said y minus y1 is equal to slope x minus x1, this is exactly the same thing. Instead of using Lx and f of a and f prime of a, we get the same. We're going to get the same equation. So I always just go back to point slope form and just find the point and find the slope and plug it in, and you'll get the exact same answers. Okay, and we'll do a problem and we'll do it both ways. So linearization function says f of a plus f prime of a, x minus a. Well, when you think about it, x minus a, isn't that just the slope, if you think about it? And isn't f of a just your y value, y1? If I put f of 2 here, well, f of 2 is just the y value. So it's exactly the same equation. It's just set up a little differently. So in this problem, it says find the linearization f of x equals x to the third minus 5x squared plus 3x minus 1 at 1, and graph f along the tangent. Okay, so if you wanted to find the linearization, we can use the formula at 1, right? Because that's what they said. So the linearization, f of 1, well, f of 1, I have to put 1 in here. So if I put 1 in here, that's 1 minus, so 1 minus 5 plus 3 minus 1. So what is that, negative 2? So this would be negative 2 here. Plus f prime of 1. Well, that means I have to take the derivative of this. Well, the derivative, that's 3x squared minus 10x plus 3. If I put 1 in here, that gives me 3 minus 10 plus 3. So that's going to be negative 4. So this becomes negative 4 here. Oops, x minus 1. So that is my linearization, which really is just a tangent line. Now, they rewrote the problem as L of x, so I could multiply through here. So that would be negative 2 plus negative 4x plus 4. Add those together, so I end up with negative 4x plus 2. Okay, that is linearization. Now, let's do the same problem, and let's say that we're going to use finding a tangent line. Okay, so in order to find a tangent line, I need a point and I need slope. Well, they already told me what the point is. They told me it's 1, negative 2. Okay, so there's my point. And we already found the slope at 1. We worked it out, wasn't it? No, I forgot what it was. Negative 4, wasn't it? It's negative 4. So if I use point slope form, I've got y plus 2 is equal to negative 4, x minus 1. But it doesn't look like it's in this form yet, but just solve for y. So I bring the, so I've got y plus 2 is equal to negative 4x plus 4. Subtract off 2, y is equal to negative 4x plus 2. Exactly the same thing. So I'm not exactly sure why they say to do linearization, because it's exactly the same thing as finding the tangent line point. So whenever I see linearization, I just think about, hey, I'm just going to write an equation of a linear function or a tangent line at that point. So here's a problem. It says, what is the linearization of f of x equals e to the x when x equals 1? Okay, so you could do it both in 2 different ways. I'm always going to stick with the tangent line. So basically the same, this thing is asking, what is the tangent line when x equals 1? So if I wanted to find that, the point, I know x equals 1. So if I plug 1 in here, e to the first power is just e. So my point is 1 comma e, which is kind of a weird point, but that's okay. And then my slope, well, if I take the derivative of e to the x, derivative of e to the x is just e to the x, put 1 in there, my slope is e. All right, so if I write my equation, y minus e is equal to e x minus 1. Well, none of my answers look like this. Kind of. I think that one looks kind of like it. So I'm just going to multiply through here. That's e to the x minus e. So now I'm just going to add e to both sides. So I end up with y is equal to e times x. Negative. Oh, no, I don't know why I have a negative there. That's an equal sign. Sorry about that. So y is equal to e to the x. And that's my answer. So linearization, anytime you see the word linearization, you should just be thinking that is an equation of a tangent line at that point. That is it. Linearization and tangent lines are exactly the same thing. L'Hopital's rule. Now, we talked about finding limits during the first 3 weeks of school. We were talking about limits. Limits have done their part helping to find derivatives. Now, under the guidance of L'Hopital's rule, derivatives are looking are looking to show their gratitude by helping to find the limit. Ever try to evaluate a function at a point and get 0 over 0 or infinity over infinity? Well, that's a big clue that L'Hopital's rule can help you find the limit of the function at that point. So, indeterminate form. If you're ever trying to find the limit and you end up with 0 over 0 or infinity over infinity, those are called indeterminate forms. And that means I can use L'Hopital's rule. And all L'Hopital's rule says is that if you take the derivative of the top and you take the derivative of the bottom, then plug your value back in, you get the limit of the function. That is L'Hopital's rule. It's kind of a cool rule. So here, for example, if I gave you the limit as x approaches 0 of sine of x over x. Okay? Now we already know what this is. We already know what the answer is because I told you guys to memorize this graph. The graph of sine of x over x looks like this, doesn't it? It gets bigger and bigger and bigger, and then it crosses at 1, and then it gets smaller and smaller and smaller. So we know that the limit as x approaches 0 is 1. We know that. But if we didn't, and we were asked to find the limit, okay, well, we put 0 in here. Well, the sine of 0 is 0. Put 0 in for x at 0. This is called an indiscriminate form. So I can't find the derivative just by plugging the number in. Well, what L'Hopital's rule says is that we can take the derivative of the top. Well, the derivative of sine of x is cosine of x. The derivative of x is just 1. So now, after I take the derivative of top and bottom, I can plug the value back in. So if I put 0 in here, cosine of 0 is 1 over 1, which is equal to 1. Holy cow! I get the same answer using L'Hopital's rule or just remembering what the graph of that function looked like. So L'Hopital's rule says, if you have an indeterminate form, 0 over 0, infinity over infinity, then you can take the derivative of the top and the bottom and then plug your value back in to get your limit. Caleb, does this stuff make sense? Should have. I mean, we did cover it last year. All right, so let's try some examples. And here's L'Hopital's rule. Limit as x approaches a of f of x over g of x. If you get 0 over 0, you just take the derivative of top, the derivative of the bottom, and then plug it back in. So here, if I was going to do this problem, if I put 0 in here, I end up with sine of 0 over, and if I put 0 here, 4 times 0 is 0, so I end up with sine of 0 over 0, which is 0 over 0, indiscriminate form. So now I take the derivative of top and bottom. Well, the derivative of sine of 3x, isn't that cosine of 3x over or times 3? Kind of have to use the chain rule there. And then sine of 4x, well, that's cosine of 4x times 4. So now if I put 0 back in here, I end up with the cosine of 0 times 3. Well, cosine of 0 is 1, so 1 times 3 is 3. Then if I put 0 in here, 4 times 0 is 0, so cosine of 0 is 1 times 4. Huh, look at that. I end up with 3/4 for my answer. L'Hopital's rule helps us find the limits of functions. Okay, let's try this one. If I put pi in here, I end up with pi minus pi, that's 0, over sine of pi. Well, pi is 180, sine of 180 is 0, so I get 0 over 0, indiscriminate form. That means I can use L'Hopital's formula. That means I take the derivative of this. Well, the derivative of x minus pi, that's just 1, over the derivative of sine of x is cosine of x. Oops. So now if I put pi back in here, cosine of pi, well, cosine is like this, isn't it? Cosine of pi is -1. So I have 1 over -1, which is -1. That is it. No. For this problem, it gives you the limit as x approaches pi. It always is what we're trying to find the limit as it approaches something. Okay, it doesn't have to be 0. This one, yes, it gave us the limit as as x approaches 0. But this one, it gave us the limit as x approaches pi. It does not have to be 0. I mean, it can be anything. It's just when you plug it in, you know, pi minus pi, that's 0. Sine of pi is 0. So that's an indiscriminate form. So now I have to take the derivative of top bottom, but then I still plug in pi, because that is where I'm trying to find the limit on this problem, is as it approaches pi. All right. Now, these types of problems, when I have infinity, I never use L'Hopital's rule, because when you have infinity, remember, infinity, the limit as x goes to infinity is super easy. You either have small over big, which is equal to 0, or you have big over small, which is infinity, or you have the same powers on top and bottom, and then it's just the numbers in front. So in this problem, you know, I'd look at this and I'd say, oh, heck, I've got the same powers. I'm going to infinity, so that's just 1 over 7, right? That's, I would never, as I said, I would never, ever use L'Hopital's rule if it's a polynomial over a polynomial and you're going to infinity. Well, anytime I'm going to infinity, I would. Because in this problem, I'm going to infinity, and it's like, oh, this is going to be a small number. This is going to be a very big number. Why do I know that? Because anytime you have x in the exponent, this is going to get really big, really fast. This, not so much. So I've got small over big. So I've got like 1 over a million. Well, that's 0. Now, let's use L'Hopital's formula on it, okay? Let's see if L'Hopital's... Now, you can use L'Hopital's formula over and over and over again, because in this problem, you would end up with infinity over infinity, so it is one of those problems that is indiscriminate. So I would take the derivative of top. Well, the derivative of top is 5x to the 4th. The derivative of the bottom is e to the 5x times 5. And then if I put infinity in there, it's going to be infinity over infinity again. So then I'd have to take another derivative. So this would give me 20x. It's 20x to the 3rd. And this would give me e to the 5x times 25. And then if I put infinity in there, it's going to be infinity over infinity again. So I take another derivative. Can you see? I'm just going to keep taking derivatives until the top crosses off. And then the bottom is going to be really big. So it's going to be small over big, which is infinity. But you can use L'Hopital's rule over and over and over again if you just keep getting an indiscriminate form for your answer. All right. How about this one? I'm going to let you work on it by yourself and see what you get for an answer, okay? Since you're the only one here, you're going to have to do both of the problems. Well, Caleb, you do the top one, I'll do the bottom one. Okay, so, and I'll talk through it. If I did the bottom one, I end up with 1 minus cosine of 0. Well, cosine of 0 is 1, so this is 1 minus 1, so the top is 0. The bottom, well, if I put 0 in for x, I get 0. This is indiscriminate. Okay, so that means I can take the derivative of top and bottom. Well, the derivative of negative cosine is positive sine of x. The derivative of x is just 1. So now if I put 0 in there, sine of 0 is 0 over 1, which is 0. 0 is a solution. The first one, you ended up with 2. Okay, so I put 0 in there. So this is going to be cosine 2x times 2. The derivative of the bottom is just 1. So now if I put 0 in here, I end up with 2 over 1, which is correct. Yeah. Very good. So L'Hopital's formula to find limits. Evaluate the limit as x approaches 10. Well, if I put 10 in here, you can see you're going to end up with 0 over 0, because 10 minus 10 is 0. 100 minus 100 is 0. Okay, so now I have to take the derivative. I probably would have multiplied through by negative 9. So that would give me this on top, just because it's easier to take derivatives. So now if I take the derivative, I end up with negative 9 over 2x. Now if I put 10 in, I get negative 9 over 20. That is my derivative. How about this one? If you put 8 in here, I'm assuming you're going to get 0 over 0, right? Because you're going to get a 0 down here. So then take the derivative, so that's negative 4x. Oh, I think this is supposed to be an x here. I'm almost positive. Well, maybe. I think it must have to be. And so then I would just take the derivative, and I get 4x minus 25, or plus 25, over 1. And then just put the 8 back in. That's negative 40 plus 25. That's negative 15 over 1. And that would be my answer. So finding derivatives using L'Hopital's rule. Oops, same problem. Nope, I think we did this one also. I think we came up with 2 for an answer, right? Last problem of the day. It's all yours, Caleb. What would you give for an answer here? Letter B. All right. I did not do the problem yet, but I'm looking at it, and if I put pi in here, that's going to be 1 minus 1, which is 0 over 0. So yes, I can use L'Hopital's formula. So if I take the derivative, I end up with negative sine of x over, and then the sine 2x, that's going to be cosine 2x times 2. So if I put pi back in here, okay, the sine of pi, I'm just trying to do this in my head. So the sine of pi is 0, isn't it? 0, 2 pi, pi, yeah, sine of pi should be 0. And then this would be, if I put pi in here, that's 2 pi, that's 360. Cosine of 360 is negative 1, so negative 1 over times 2 is negative 2. But I'm going to go with 0 for my answer, because the sine of pi, oh, that's negative sine of pi. Well, negative sine of pi is 0. So I'm going to go with letter C. I'm going to disagree with you there. I could see how you got that negative 2, but the top is going to end up being 0 there. Does that make sense? Oh, kept the 1 in the derivative. Okay, Caleb, that was it for today. Not a whole lot for this week, since it is a short week. All right, so if you're not feeling well, Caleb, go and take a nap. Have a great week.